afternoon, everyone. I hope you enjoy the conference, and thanks so much Thomas for the introductions. What we want to present today, it's a bit new. So first of all, please bear with us. We might have some, I would say, beta things or things that are under experimentations right now, so don't blame us for that. It's basically the first time that we do this presentation about this topic. So I'm Alexandre Dulaunoy and Jean-Louis Huynen. We are both working at CIRCL. One of our objectives at CIRCL is basically to produce tools for us, but tools for others. Open source tools that everyone are using, and especially to make the place a bit better, especially in the CTI world. So we do MISP and other tools. But really the idea today is really to share with you what we are working on and maybe to improve this process. And if you have any feedback and so on about this crazy idea and crazy process, don't hesitate.
Yes, so the idea is to try to, because it's a practice we have, we use some filters in security, and Bloom filter in this case, so we are not the only one. There are people at DCSO, for instance, or Tenzir using these kind of filters, and we want to formalize the thing and like describe this thing so we can share it and other people can do the same thing. So as an introduction, I will try to introduce Bloom filters. So if you know Google Safe Browsing, it's a service that has been bought by Google in 2007, something like this. And the first version implemented a Bloom filter so for the users to check before reaching a website whether or not it may be malicious. So the Bloom filter data structure, it's a probabilistic data structure. So the idea is that it can, so it's like a set, it's like a list. And when you do a query on this list, it will give you the answer, yes, maybe, I know this value, or definitely not. So that's the thing. So the way they used it in Google Safe Browsing is that the user was trying to reach a URL, was doing the request on this Bloom filter. Then if maybe it was malicious, it would then reach Google's server to actually know if it's really malicious, to just remove the doubt whether or not it was a false positive. So then they had different constraints that we don't have because I think between space and speed, they chose speed, basically. So now we are at the 5th version and they don't have the Bloom filters anymore. But we believe that this kind of data structure could be used for CTI in security, and it's actually something that could be important. So.
And then it's not really coming from nowhere. So we're not just popping up here and saying that we do something completely new. It's basically something that we were experimenting for years. As you know, MISP core functionality is sharing. So sharing indicators, sharing information, and so on. And that's really something that we wanted to do from the early beginning, is to be able to share information without actually disclosing the information to third party. We have plenty of use cases for that. We will come back to the different use cases. But in 2017, we basically started to have a first implementation. So I think for MISP, and I think someone from Siemens clearly explained it, we basically experiment a lot of features and testing it until that we come to kind of finalize features. And in 2017, we started a project called MISP Privacy Aware Exchange. It's still on GitHub. It's not part of MISP, but it's an extension. It's based on a paper from Van de Kamp in Netherlands. We basically did a paper for actually sharing private set of IOCs using different techniques, and that was the first implementations. Then later on, we had another project with a research center in Netherlands too, where they actually basically work on MPC, so it's called multi-party computations. That's not really the topic of today, but it's something that we were thinking that was a good idea. But finally, we discovered that it's not a good idea. It's basically highly costly and complex to use. You basically need to be connected online, which is basically one of the most interesting features with disconnected data set like Bloom filters and so on. It's to be basically able to do your queries without querying any services on the internet or remotely. So that was really the first evolutions and tests that we did. But that's this one set up the ground for the additional research. On top of that, and filters, it's not a secret for you. I think many of you are dealing with IOC lists, indicator of compromise, selectors, attributes, observables, and so on. So on a day-to-day basis, filters are everywhere, in TIP, in various tooling. It could be in network intrusion detection systems, and so on. They are actually used to do detections. They are using sometimes for doing skip lists. So for example, to have allow lists. It could be detection rules. It's the lists and structure that are already used. So Bloom filter-like structures and probabilistic structures are already used in many security tool sets. Suricata and so on are using it, and it's very common for that. But the thing is, and that's what's really attracting us to go in those kind of structures, so that's why we evaluated first other structure that looks like more advanced, but technically, we came back to Bloom filters. Bloom filters are pretty old. I mean, the original academic paper about those filters are from the 70s, so it's not, I would say, a very new technology. But nowadays, it's very practical and you can use it, and this has plenty of properties that you can use for actually sharing your indicators. I'll take an example. You are a CTI provider. You are providing feeds, and you share those through MISP. But MISP might be connected with other MISP instance. And then you might share back your vendor-only indicators with third parties. So vendor of CTI might be afraid of that. And what we wanted to do is to find a solution where you can watermark the data. So that means that you can even trace where the original filter is coming from without disclosing the filters. And that's those properties of probabilistic data structure that Jean-Louis mentions for like the Google Safe Browsing allow such kind of things. And for example, it can be offline too. So we basically try to combine everything that we have seen on the past, in the past year and to come with something that basically work and have all those properties.
Yeah, the thing is that all those data structures, like for instance LRU caches, it could be useful, for instance, just to find a way to serialize this thing, describe this thing, what's inside, how to use it, and then share it to someone else so it's ready to use. So for instance, you could imagine, for instance, you have a big MISP instance with a lot of sightings that you update quite a lot. So you have a lot of SQL queries. You could actually use LRU caches that are kind of ordered lists of indicators from which you drop all the things that you didn't see for a while, and then you could actually share this with another instance instead of marking sightings. We could imagine these kind of use cases, for instance. So yes, there is the confidentiality, privacy, watermarking if we, for instance, put an HMAC on what we put inside. Also working offline, so a lot of things like this. Also private set intersection, as we tried to introduce just before. If you use Bloom filters, there's a way to, for instance, you could imagine having a Bloom filter for one event and another event, and then you kind of compute the Jacquard index, the cardinality of the intersection of both sets. So that could be very useful to know if on another instance or another event, if there are some similarities, and then maybe decide to share openly or not, or something like this.
So there are plenty of properties that we can use in CTI, and that's what we try to basically do. And Jean-Louis mentioned something very important is serialization. So that means is the act of creating data, data structure that you can basically share with others, which is in a generic format. And I think there are some people from DCSO here. We basically started to use Bloom filters, and we use the serialized format that has been proposed by DCSO, and thanks to them for that, called Bloom, which is basically a library in Go for creating those kind of data structures.
That was basically the only one that proposed to serialize the structure in memory on disk. So that's why we choose this one. And also there was a Python implementation. So that was like a good first step for us to use in our tools.
Yeah, thanks to them, because it was really a kind of first step.
The enabler.
Yeah. So as we use the DCSO implementation, we use it for a real use case. So we started with services that maybe some of you know from CIRCL called HashLookup. So basically HashLookup is a database of what we call goodware So if you are doing forensic and you don't know hash lookup, I really advise you to have a look at it. It's a way you can query to a web services to check a hash, to know if this hash is already known into a classical distribution of operating systems, and so on. Very useful to basically do triage on forensic analysis. But a lot of investigators ask us, oh yeah, but I don't want to use the web services, it's slow, I want to keep my queries private, and so on. You have to do something about it. And then where it's basically the first DCSO Bloom filter usage, it's basically to come with an export of all data set into a Bloom filter. So right now there is a Bloom filter of around 1 gigabyte that you can use to load into your system and do automatically search to see if you have any match on those lists. And that's really the first use, and this one is a real case usage, it works, and so on. Jean-Louis did expansion in Yara, maybe you want to...
Yes, here the idea was like, okay, if we can have a way just to remove everything we already know, that is good. Maybe we could already do that in Yara. So like Alexandre was on vacation for 2 weeks. I said, okay, I can try something that maybe I will fail to do. So I wrote the library in C to write a Yara module to do that. And it actually works. So then you can just, the first step, you filter out whether or not you know this file. And if you doesn't know, then you have your whole pipeline to identify the file. That's the idea. And then we have ALE project. So I don't know if you know the ALE project, but it's a tool we have to crawl the darknet, Telegram channels, a lot of different sources like this. So we get a lot of unstructured data. And out of this, we want to just keep the things that could be relevant to us and our constituencies. So we have filters, so Yara rules, set of words, regexes, to grab all the interesting things in there for us. And now ALE project uses Bloom filters to keep some data, like to keep some records. For instance, if there's something that you tag as harmful content, something like this, you could put this in the filter and then give this filter to someone else in order to them to protect with these filters without being really able to enumerate what's inside the filter, but they can still use it to protect themselves.
One of the examples is child abuse materials. I mean, if you are a forensic investigator, you really don't want to look at that content, and basically creating those Bloom filters help to filter out such kind of data. So when we started to use it, we were like, we did some different implementations, but after different discussion, we came to say, well, but we want to facilitate the sharing of that. I would say the DCSO Bloom filter was a good start, but we want to facilitate that if I have a filter interesting, I could share it with you, and you know exactly how to use that filter, and basically to make an active use of the data that we are sharing. So what we decided to do is to basically normalize and build a standard, which is super simple, to describe the data set, so the filter that you have, which is usually a binary file, so serialized files with data structures, but you want to make it accessible to others, and we basically created a meta format, which is basically encapsulate how the format is described into those different files, and how you can use it. If you are curious, it's already on GitHub. It's, I would say, beta. We are more than eager to get feedback from CTI teams, CTI vendors, and others that would like to use such kind of format. The format might change a bit, but I think we have already a good basis to make it work for different solutions. So to just have a kind of, I would say, overview of how PSS would be used and so on, it's pretty straightforward. You have basically producer that will generate PSS files from different ways. So you mentioned ALE, it could be one source. So for example, we can have specific data that we collect from ALE. We could have things that are indicators in MISP, context, Yara rules, for example, things like that. Or it could be an analyst that generates such kind of list. And the PSS files is basically composed of two parts. It's composed of a part which is the actual metadata, so small JSON files describing what's inside, and then you have 1 and one or more files, which are the files that are used for basically the filter files that are used to do lookups against. And those files can be distributed, and you might have partners actually getting those files to make lookup into their systems, or you can have even user or even systems doing intersection of those files. Maybe you want to talk about the intersection aspect?
For instance, for Bloom filters, we could do intersections. But here in this example, for instance, we put Bloom filters and hash files because we started on Bloom filters because we have the use case now for Bloom filters. But we want later on, if there are some use cases for this, if you have some IDs, like for instance for LRU cache, because we already had some remarks regarding that. So we want to have additional types of data structures like this that could fit other use cases. So for instance, yes, Bloom filters, we could have the use case of intersecting between instances. So MISP is a really good fit for that. It's something that could be used. Or even if you want to do steering, if you have different MISP instances, like we saw this morning, I believe this kind of structure could be used to know what's at a glance like this, just what is inside, like you have a flat list of attributes, because from my understanding that's how it's used. So you just do steering, like it's actually like a router to route your different requests to the different MISP instances. And in routers, they use Bloom filters. So that's the same thing, basically.
So for the one that, like more the technical part of how it's built, and so technically, those Bloom filters that we are using are code-based or text-based Bloom filters, so that means we add string inside that Bloom filter. The only thing in the standard that we define is when you insert a value into it, so value could be a hash, an indicator of compromise, and so on, we basically key hashed it. So for the one that are familiar with crypto, we basically use a CMAC or HMAC functions to basically normalize the data inside the Bloom filter. We do that for different reasons. This has some cryptographic properties that basically distribute and diffuse the data. But in addition to that, it's allowing to, for example, create unique filters for different groups. So for example, if you have a partnership with, I don't know, another CIRCL, you might want to use a specific key, and you know exactly that this key is used for that users.
So then the data is tainted and you have a watermark, basically.
Yeah, and then you basically add that in those binary files, and those you encapsulate it into a PSS files to describe or you add the data. Just keep in mind it's basically that you need to canonize, so that means you need to normalize the actual data that you put inside. So for example, if you have, I don't know, domain names, is it uppercase, is it lowercase, and so on. And that's why in the format, we describe the way to normalize the data that you'll put inside the filter list. So we have an interesting use case.
Yeah, this one is a use case we have because we need to reach the Tor network to go in different forums and stuff like this for ransomware, like monitoring ransomware activities. So we have Ale and other tools that can actually point out different onions where we can go, but still to reach those things, we needed to, so before we were just using the Tor browser, but we needed to have some kind of safe for work way of using this darknet. So what we do is that we have a proxy, so you can actually skip to the next one. Like you have a proxy that you reach, like it's a Tor to web gateway, basically, which is internal. And then when you try to reach some onion, for instance, but it can also work on hashes of images or whatever, and it checks this against the filter, and depending on whether or not it is known to have certain properties, so for instance, you shouldn't go there, for instance, then it will filter this content, and then you won't see this content, and you're protected, basically. So this is one of the use cases we had.
And this one has a huge benefit, because technically you basically share in a Tor browser bundle the PSS files, for example, containing a lot of child abuse materials, drugs market, and things like that. But you don't disclose it. So that means you are safely having this protected, but only the user will be blocked when they hit a specific item which is inside this Bloom filter. So What have we done already? So the standard itself, we have a first version that has been published. We have a kind of minimal library in Python to handle the PSS meta format, to generate it, and so on. In addition to that, we have developed a new library for the Bloom filter part, which is, I think, interesting because this was an evolution of the original DCSO Bloom and solving some problem that we had previously. Within CIRCL, we have already different use cases, and I can already share those use cases with you. So one of the common ones, and is basically due to the fact that a lot of MISP users are in the financial sectors, and they start to be interested in sharing some indicators like bank account numbers. And you might know in Germany, the regulation might be strict regarding that. In some other countries, it's depending. But with PSS, the nice thing with that is you can export complete financial details, including bank account names, the bank account details, and so on, into MISP, or to export from MISP, and to import it into any tools that is doing, for example, wire transfer, banking systems, payment processing systems, to basically do filtering without actually knowing the bank accounts. And that's really solving one of those kind of legal problems that people say, yeah, I want to use MISP to do a sharing community, but I don't want to share because you know. But then you have a solution that you can actually share that. Another thing, and this one was interesting, we use Ale for monitoring a lot of keywords, and not everyone is capable of installing an Ale instance in their premises, so we operate Ale infrastructure. So instances, we are grabbing on Telegram, we go on Tor, and so on, but we need to search keywords. But a lot of organizations don't even want to give the keywords. For example, it's employee names, it could be product name, or future products that they don't want to disclose, things like that. So what they do, they can do, give us those kind of PSS files, they generate it on their site, and we can use it to basically do a lookup in Ale automatically and notify them when something is leaking or something is basically found on a forum. So that's already the beginning integration of PSS. Now we have some future works. The first of all, it's basically, we want to stabilize the format. And to stabilize the format, we want to be sure that we get the feedback of the different users. And we will write a IETF internet draft to basically normalize it. We, on the MISP development, we are working on the privacy-aware correlations so that you can basically do privacy intersections. That what Jean-Louis was mentioning, that when you have multiple MISP and you want actually to compare that. But we are interested in gathering feedback because the structure is quite flexible. You can do a lot of things, and I'm sure we are missing some idea there. Jean-Louis has some crazy plan on new data structures for LRU caches and so on, for expirations, automatic expiration of data, having sliding windows of things, and that's maybe something that we are implementing.
And in the draft, I think, so we discussed this already, but because for now, we took a shortcut, just saying, okay, for instance, this Bloom filter is in the format DCSO V1 or POPI, the one we created, V2. And if we do a draft, maybe we should actually have a complete description of what those formats are. So this way we avoid the burden of creating implementation each time, because now we have this small library, and already this is already something, it's a lot of work. So if we define clearly everything in the draft, it will be already better. So it's already something will change.
Yeah, to make it extendable so that they can extend it to the use case. So just to conclude, because I see Thomas with this panel with minutes running out. So I'm just on time on conclusions. So first of all, it's really the PSS format is to facilitate sharing of information that usually were not shared and restricted for legal reason. Obviously, we are fan of open source, fan of open standards. So for us, it's super important that everyone can implement. I mean, if we have vendors implementing into their CTI feeds, that's great. Thing that we didn't discuss that much, but there are plenty of use cases from CTI processes with probabilistic data structures like Bloom filters and others. So maybe in the future, we might come with other idea in the futures. In the slide deck, you have a complete set of references with the private search set, POPI, which is the re-implementation of the DCSO Bloom filter in Rust that we did. And there's a complete article on the MISP project page regarding what we did on the Bloom filters. And the last slide is there because I was forced to add it due to European funding. Thank you very much.
Thanks.
So are there any questions? We have 2 microphones.
Warren Kamari, Google. Could you go back to slide 12, I think it was, the one with the Tor, blah, blah, blah?
Yep.
So it's Bloom filter, so it's probabilistic. How do you sort of tune that to make sure that people get the right amount of stuff because the failure mode's potentially bad in either direction?
Yes, the thing is that we skipped the previous one, but this one is a combination of 2. You have the non-malicious, which is a Bloom filter. So if you could have false positive, which is not a big deal. You just fail to reach something. Okay, and we have also non-good lists, which is just a list because we don't care actually to keep this content, like to leak this content. So yes, it's a combination of 2 things. But Bloom filters, there are different ways. So I won't. Okay, but there are different ways to make it more reliable regarding the false positive rate. For instance, in Mozilla, they have something, in Firefox, they have something called CR-Lite. So it's kind of, you have a Bloom filter, then a Bloom filter of the false positive, and another one again, something like this, but you need to know exactly the universe for this to work. So there are different things like this. Each time you need actually to think through what you want to do, and you need to be careful. It's not magic bullet.
And it's depending on the use case that you have. For example, for the forensic part, what we do, we reduce a lot the false positive ratio against the space. So the space is bigger, and then we have this ratio that we use. So it's really depending, and it's usually combination, and depending on the use case, you need to fine-tune that. Yeah.
But to try some crazy things, for instance, we took from the warning list, the list of the like Tranco, 1 million websites. We generated all the permutation of typo squatting possible. So it's like an average 6,000 per entries. And we built the Bloom filter with that, which is like 9 gigabytes. And inside you have 6 billion entries. So then you can filter out everything that could potentially be some typo squatting on something from Tranco. So, but then you have to have some strategies to keep this in memory, be able to do your requests and all. So it depends on the implementation. That's quite cool.
Thank you very much. Is there one more question? Last one, maybe? Okay. We are still there, so don't hesitate if you have any questions. Thank you.
Thanks.